Hello, everyone, and welcome back to Perceived 2021. Please give a warm welcome to our distinguished guest, Yuchen Fama, Ph.D., Director of Product here at Clarifai. Yuchen is going to be speaking about machine learning techniques of time series data and deep anomaly detections. Yuchen, welcome to our stage.
Thank you, Jeff. So for this talk, I'll give a brief overview of machine learning techniques of time series data with the focus on deep anomaly detection applications with some empirical examples. So the motivation for this talk is that in the past decades, most of the deep learning research and applications have been focusing in areas such as image recognition and natural language processing. And in recent years, increasingly, we've seen this explosion of industrial 4.0 and also with the IoT data and in the time series form. So in industry verticals such as such as manufacturing and also industrial side, they're really our target industries at Clarifai. And so that's why it's important that we provide a really best-in-class solutions to our customers in terms of anomaly detection and predictive maintenance. So the agenda today are 4 parts, and we have first the very brief overview of machine learning techniques of time series data. I'll focus more on very simple kind of mathematical intuitions and just highlighting a few popular techniques. And then we'll talk about deep anomaly detection algorithms. And then we'll briefly talk about uncertainty quantifications of deep anomaly detection and with an example of predictive maintenance example. And it's an empirical example with a few kind of practical tips, because oftentimes to link this optimization function with your business ROI to really have that tightly integrated, we need to design specific optimization functions to weight the false positive and false negative with the business cost of each, so that we can really optimize towards the business ROI. So I'll give examples like this with just more details for this particular application. So in terms of machine learning techniques for time series data, it's very important to understand the basic key characteristics of time series data. And because it's important to understand the problem before we jump into fancy architectures, etc. Then we'll talk about classic time series model, because time series models have been around for many, many decades. They're still very, very popular, very accurate techniques such as ARIMA that's been heavily used in many time series, especially forecasting applications. We'll also talk about state space models and hidden Markov models, and they really kind of inspired the modern deep learning, especially the sequence learning techniques such as RNNs with really this type of parameter sharing philosophy behind it. And not for today's scope, but there's another broad kind of a family of frequency domain spectral analysis. And if the audience is interested, please feel free to look it up. So from classic time series, we want to move on quickly to the deep learning models, because oftentimes for anomaly detections, these classic time series models have certain limitations. So we'll talk about popular techniques such as autoencoder and also the probability spin on top of it, which is variational autoencoder, which is very, very popular anomaly detection algorithms, but it doesn't have this temporal components. So we'll also talk about LSTM autoencoder, where we encode LSTM in the encoding layer, and a semi-supervised version on top of it, on top of variational encoder, which is the conditional variational encoder, if we have time. And definitely not for today's scope, but also very interesting probabilistic deep learning models are, for example, stochastic recurrent neural networks and deep autoregressive models, but they're not in today's scope. If audience is interested, please feel free to look it up. So time series data, technically they are time series, they're collections of realization of random variables indexed over time. So you can think of it almost like a stochastic processes technically. And we have many different applications besides anomaly detection. For example, forecasting, time series forecasting, especially for financial time series, is very popular. From, for example, sales, revenue forecasting, from the stock price forecasting to econometrics, for example, the GDP growth, and very powerful applications there. And also in the field of scientific fields such as physics, where this unevenly spaced data, sparse data, and also missing imputation needs a lot of more precise techniques. So we also have a lot of applications, particularly in functional data analysis for this time series data. And generally, we also have clustering, basically techniques where you can try to, so the idea is that we want to disentangle and understand the underlying source of variation in the data generation mechanism, and how the pattern, on top of a manifest that mechanism. So for example, if you have a group of very heterogeneous sensor readings, and you can do the clustering like in this, bottom right example, and you can see, certain clusters may share some, common characteristics, and they're not captured in your metadata, but then from the clustering, you can actually find those similarity and dissimilarity characteristics to better understand the data. So there are a variety of classic time series models. So for today, we're going to talk about three. There is a ARIMA model, and also I want to talk about hidden Markov model, and also the state space model. So ARIMA model is very classic even till today. Even though it's been around for decades, it's still very powerful, very accurate, and it's just very classic. And the idea behind it is we have several pieces. The AR stands for autoregressive. So what you see here with AR with lag P, basically the idea is that I want to model this particular time series based on kind of a linear combination of the previous lags plus a Gaussian white noise. And also, there's another term, MA, which is moving average. And the idea is, well, for the Gaussian white noise, it also can be modeled based on a linear combination of the lag terms. So you actually capture this kind of sequential dependency, which is the nature of time series data. And that's why you can't just throw in, say, modern, machine learning techniques for structured data like XGBoost or random forest through time series data, because inherently there's a time dependency of it. So this type of characterization is very helpful if once we estimate the parameters such as theta and phi. So this is the ARMA model setup that is essentially based on the lag terms. And the I in the middle for ARIMA stands for integrated. So it's autoregressive integrated moving average. So the idea behind it is that, for ARIMA, the assumption is a stationary sequence, but oftentimes in real life, you can't find, it's very rare to find stationary time series. Oftentimes is non-stationary. And to handle that in this case, if it's a non-stationary, random walk here, xt equal to xt minus 1 and plus omega t, then you take the difference of it. So the difference is stationary in this case, because then you kind of just, difference out and then leave this white noise. So it's a very simple, elegant idea and actually work very well. And it's not just the only way to make the non-stationary data stationary. There are other techniques, for example, hidden Markov models. So hidden Markov model actually, okay, sorry, state space model. Actually, they're very similar between state space model and hidden Markov model. So many structured time series models, such as ARMA, they're valid if, as I mentioned, the observed time series is stationary, or at least joint stationary, or like a ARIMA case, you basically transform it into stationary by detrending or deferencing. Detrending has some other techniques like ETS I'm not going to cover today, but it's also very simple, just functional kind of transformation to make time series data stationary. And but oftentimes for non-stationary time series data, there's a more natural way of modeling this by constructing the model with time varying unknown parameters. So the idea is that we have a latent state and then we have observed equation. So the latent state, which is unobserved, we in this case, in a state space model, for example, we can use AR1 basically with one lag terms to model this station equation. And on top of it, you can also have a observed kind of function, which is YT. And YT is a function of XT and also plus VT. And then we also have some normal distribution assumptions. So this space-based model is actually very, very popular in fields of, for example, physics. And also it gives a lot of really nice properties, and you can literally analyze a lot of the stochastic systems with stochastic processes with the state space model, especially in engineering control system and computer science, etc. And actually, as a matter of fact, I think Kalman filter is a special case of state space model as well. And there's another special case of state space model, which is the hidden Markov model. So hidden Markov model, as I mentioned, it's a special case in the sense that actually the underlying state is discrete, versus for state space model, it could be discrete, it could be continuous, and also the underlying state satisfy the Markovian properties. Markovian property, basically in layman's term, is memoryless, which means that if you make a prediction, it really depends on your current state, or your current state really depends on the previous state. So for this stationary Markov chain, really what we call like a transition matrix, is time independent. This is very beautiful property, so you can actually, is analytically solvable. And as you see in this little diagram, the hidden Markov model has also observed variables on top of the state, and you can actually tell that this really inspired a lot of the modern deep learning architectures of, for example, the sequence learning architectures like RNNs or LSTMs, where you have really kind of this latent state kind of representation. So you can actually have a parameter sharing instead of just modeling kind of joint probability distributions of every single time series variable, because each time series point is the realization of that variable. And instead of modeling the joint probability distribution, which is almost analytical infeasible, you can use this parameter sharing and then the underlying state to borrow this statistical strength from the past observations. So I don't want to spend too much time on the classic methods, because there are limitations of classic methods when it comes to the IoT time series data. Because oftentimes, especially if we talk about machine sensor readings, this type of IoT, high velocity IoT data, oftentimes is non-stationary, and the anomalies are also very rare events. And you also have really different type of anomalies. You can have this contextual anomalies, where you have a period of really just an anomaly, and then you kind of drop, versus a single shock type of anomaly. And also, it's very difficult to do like a hand engineering, feature engineering in many, especially industrial anomaly applications, detection applications, because basically hand curated feature engineering is just not feasible. And that's why deep learning has been so popular, because if you have higher enough capacity, you can automatically capture the pattern, rather than analyzing all the error kind of lag patterns and try to understand what type of lag you need to have, how many parameters you need to estimate, and for what type of lags, and lots of really kind of statistical kind of data processing and XOR data analysis and error analysis, and doing all sorts of goodness of fit tests to eventually specify the model. So in this case, deep learning is beautiful, where you have just this automatic capturing, if the model capacity is high enough, you can automatically capture this pattern. And also another challenge is that oftentimes the real-time time series modeling, you need this constant monitoring, update, and with a lot of classic methods is also a challenge as well. And so that's why deep learning model has such so many nice properties to handle real world anomaly detection problem, but there are also challenges associated with it as well, which I'll elaborate in the next few slides. So talking about the deep learning anomaly detections it's a mouthful, so I'll just use that, which is a deep learning anomaly detection. And when it comes to different families of DAD, there is unsupervised DAD, and there's a semi-supervised DAD, and there is a supervised DAD. So I always joke about this analogy to, my husband when my son was born. Of course, with a young baby, first of all, he was a very supervised dad, then he grew into a semi-supervised dad, and now he's an unsupervised dad. So unsupervised dad here, basically the idea is to learn the best representation of the data, and based on empirical prediction of the error distribution of the reproduced pattern versus actual pattern, you can really plot basically this empirical error distribution of this delta, and then you can set a threshold, say 5% the tail, and then anything above that threshold will be anomaly. Because the beauty of unsupervised learning is that you learn as much as you can from this, the best representation, and then you reproduce the pattern, because that's the estimation problem. You really produce the pattern and you compare the actual versus the reproduced, and then plot the delta and then look at the threshold above, say, a certain set number. So this is very useful and practical. And because unsupervised approach, oftentimes the nature is that you don't need a lot of labeled data. And the nature of anomaly detection is because it's anomaly, so you really don't have much labeled data. So they work really well together. But as you start to accumulate some labeled data, there's also a semi-supervised deep anomaly detection. The idea is that you try to learn the discriminative boundary around your normal case versus anomalies. So the conditional variational encoder I mentioned earlier is a kind of semi-supervised learning where you basically concatenate the label into your the encoded layer, and you basically that's a way of kind of incorporating the label data in your learn approach. And supervised that is very rarely used because, as I mentioned, the nature of anomaly is that you don't have much label. And really the idea is to train, of course, deep supervised, either binary or multi-class classifier with label, but in this case, it has very limited applications. So for the rest of the talk, I'm going to focus on unsupervised DAD. So when it comes to unsupervised DAD, autoencoder is pretty much one of the most popular kind of a family of architectures. And essentially, autoencoder, they belong to a family called generative models. The idea is that if given the training data, you can generate new samples from the same distribution. And it's a classic density estimation problem. And then in terms of density estimation, I think, autoencoder, specifically variational autoencoder, is a more explicit density estimation versus, popular methods like, again, is more implicit. So in this case, especially for anomaly detection, where you need a little bit more kind of reliability, you need a little bit more kind of, probabilistic, more grounded probabilistic and framework with good mathematical kind of framework, then I think BAE is better than GAN, especially in my opinion and my previous experience in industrial applications. And for autoencoders, I think, as we all know, it's an unsupervised approach. You basically learn a low dimensional feature representation of unlabeled training data. And the analogy to classic, statistical methods is like a kernel PCA, which is a nonlinear PCA. And the graph on the right-hand side shows basically the intuition is that you have this mapping from your input data and your output data. And there's a underlying feature space, and you basically can have a encoder network. Of course, it doesn't have to be deep neural network. Decades ago, it could be just very basic kind of linear functions, but then you literally right now is mostly the deep neural network, where you have that in the encoder network from input data and map to the feature space, and then you have a lower dimensional representation of the data, and then you use a decoder network, and then of course you compare the output data versus your actual, and then compute the L2 loss function to do the density estimation. So for autoencoder, especially application anomaly detections, as I mentioned, anomalous events, they're really rare. And a well-trained autoencoder, they can really produce a very good representation from the normal process. And oftentimes, actually, people use autoencoder as a denoising kind of a network, because it works really well when it capture this really the true kind of a pattern of the data. And also it's important to know that if the reconstruction, as I mentioned, if your reconstruction error is high, then you label as anomalous event. But the problem is that there is also limitation with autoencoder, and because it doesn't use the temporal feature in the data. Oftentimes in time series data, you have to basically, you don't want to waste this signals based on the temporal feature. So I'm not gonna talk too much on the recurrent neural network, because it's very, very classic. Most people are familiar with that. And more, I think recently, the LSTM, which is more popular, in terms of temporal or sequence learning. I also don't want to spend too much on this, because LSTM also is pretty ubiquitous in the sequence learning. And if audience want to look it up, feel free. But basically, it has a short-term, long-term memory, and it's very popular when it comes to sequence learning. Now, what I do want to talk about is that typically you see in anomaly detection, you have LSTM, and of course, LSTM is also in the old days before we have transformers, also very popular in natural language processing. But you also have autoencoder as a very powerful, anomaly detection algorithm. So in my previous research efforts, we actually tried autoencoder in the we tried the LSTM cell in the encoding layer of the autoencoder, and it worked very well. So it has the best combination of the two. So the idea is that basically the LSTM autoencoder, as I mentioned, it's very simple. We have the encoder decoder LSTM architecture in your autoencoder. Of course, it doesn't have to be both encoder or decoder, and oftentimes in the encoder itself it's good enough, and it can learn a compressed representation of the sequence data. And basically, the encoder LSTM, the way it works is it reads in the sequence, and after the last input has been read, the decoder LSTM will take over and output predictions for the target sequence. Now, so LSTM autoencoder worked pretty well, actually. In my previous experience, we put in production, also worked pretty well. But then there's another challenge that, oftentimes with deep anomaly detection algorithms, there is also a kind of uncertain quantification need, because especially if it's a really expensive industrial machines, nuclear power, plants, for example, when you send, alert, the cost of both false positive and false negative are also pretty high. And you want to make sure you have some uncertainty quantifications around it that has a good kind of mathematical foundation. And in general, uncertainty quantification is a challenge in the field of deep learning. So in this case, in this presentation, I'll cover two most useful and also very, very simple methods that are proven, effective in many, many applications in the real world. So the first one is the variational autoencoder. So I mentioned a few times in my previous slides where variational encoder is basically probabilistic spin autoencoders. the idea is, by the way, I'm a Bayesian, so I'm super excited to talk about anything that's Bayesian related. So the idea is you have a priority distribution P of Z to be Gaussian. And of course, Gaussian has so many good properties. And also, when you talk about Bayesian conjugate priors, etc., and it's just very powerful. So that's why, it's literally for variational encoders, Gaussian is chosen to be the prior distribution for P of Z. And you also have a conditional kind of a distribution of Px given Z. And here's the data likelihood. And based on the very famous classic Bayes theorem, you can also estimate the potential posterior density of PZ given X. So this is a really classic Bayes rule. So the problem of this posterior density is that it's intractable because you have the integral of that of P of X here in the denominator and also in this conditional density as well. So how do we solve this problem? Is technically analytic intractable. So there's really a classic, variational Bayes, and that the idea was borrowed by a lot of deep learning researchers because the variational Bayes was a very classic family of this Bayesian machine learning. And the way the idea is that instead of estimating this posterior density, we'll estimate the lower bound of this posterior density, because you can decompose this equation into several components, and then using the property that KL divergence, this KL function is always greater than 0, you can actually estimate the lower bound of this posterior density. And so we call the evidence lower bound of the data likelihood, and you can optimize that and direct gradients, etc. So in this example, I think in addition to the previous example of autoencoder, for variational autoencoder is that you now can sample from the true prior distribution, and you can sample from the conditional distribution, and then you can really generate the data. And also based on the data generated, you can estimate, for example, mean the variance easily from variational encoders. And there is another even simpler approach for uncertainty quantification, which is Dropout as a Bayesian approximation. So the idea is also very simple. Basically, you use a Monte Carlo forward pass, and then you obtain the sample mean and sample variance. So what it doesn't mean is that when you do the forward pass with the Dropout, and you just run many, many, many times, and then you take a look at the the actual output, and you just compute the empirical mean and empirical variance. So the idea is so simple that oftentimes people question, does it really like how does it work so good? Actually, someone brilliant, I just quoted a few publications below, actually mathematically derived that this seemingly kind of very, very empirical approach actually has a elegant mathematical kind of a approximation of the kind of classic Bayesian machine learning framework. So it actually has a really, really nice kind of a property behind it. And also the other kind of a minor improvement on top of it, or you can argue, it's major, is that because you have to run so many dropouts, it may not be very efficient, especially, when you do the kind of inference time uncertainty quantification. So I think there's another paper that is also pretty helpful, that basically is the same idea, but then you use a dropout distillation where the teacher will maximize the accuracy, but they also train a student network to learn from the Monte Carlo forward pass from the teacher. So these two techniques are very, very useful, and hopefully, you can give it a try. And but in the last few minutes, I also want to highlight a few examples in the real world kind of predictive maintenance examples. So, so the data is collected from kind of a university lab temperature sensors, 15-minute sampling for 30 days, and then we train basically 20,000 points, and also reserve some points for the testing. And then it's very simple architecture, 4-layer encoder and also 4-layer decoder. And as you see, I think I want to mention that the most important piece actually is the bottom, because the beautiful graph shows here on the bottom left, you can see, on the lower dimensional manifold, you can see the anomalies in red here. Very, very beautiful. And on the right hand side, you see the, also this beautiful, almost like an artistic representation of different patterns captured in different colors. So there are 4 colors representing the 4 time range during the daytime. So it's a 4-hour, or 6-hour block during the daytime, and then you can see very distinct patterns during that time. So you actually kind of unveil some of the patterns of the sensor reading based on the time of the day. And I think the important piece is that, this high, when we mention the data lays in the manifold, different time slots or different kind of manifold, it's important to choose the right dimension manifold to have the representation. Sometimes you trial and errors. You can try, 5 manifolds or 10 manifolds until you can have very, very obvious pattern. So in the next example, oops, sorry. It shows basically a 2-dimensional, 5-dimensional, and 20-dimensional manifold. And as you see, for lower latent space dimension, the manifold is really less clear. So I know I'm running a little bit out of time. So just to summarize for this talk, first, I think it's important to really understand your time series data before you choose architectures, really understand the empirical, the data, and then understand also the basic kind of applications. Do you really need deep learning kind of architectures, or the problem is simple enough? For example, in many social economic time series, you can easily capture, the seasonality, the trend with very basic kind of parametric functions without jumping to the, deep learning hoop. But if your data time series data is really, for example, in anomaly detections and just have such an, subtle patterns, and also it's hard to, do the kind of classic time series modeling with hand featured and, the hand engineer features, then I recommend the kind of deep learning approach. And also for the deep learning approach, both autoencoders and LSTM work pretty well, but if you combine the temporal components with this, really beautiful autoencoder framework, you can actually have a really powerful results. And finally, for uncertainty quantifications, both variational encoders and also Dropout as Bayesian approximation work really, really well. So with that, I'll just close this talk and hope you enjoyed it. And so thank you so much.
Thank you so much, Dr. Fama. It's always a pleasure to listen to you speak about your work. It's some fascinating stuff. And a big round of applause from our virtual audience. Thanks, everyone, and we'll see you at our next session.